right, good afternoon, everybody. Thanks for having me here. My name is Jordan Tigani. I'm engineering director on Google BigQuery. I was one of the first engineers on BigQuery when we sort of were just still trying to figure out what to build. And I've sort of been riding the BigQuery wave for the last 7 years, and it's been pretty exciting. I'll be joined by Lloyd Tabb, the CTO of Looker. I'll tell you a little bit more about Looker when we get to his part. But in my opinion, the best innovations come from when you break constraints, when you have a wall that seemed insurmountable, so insurmountable that people sort of forgot it was there, and then all of a sudden that wall is gone, and all of a sudden then you can do all of these creative things with it. Here's an example. How many people had a phone that looked something like this? Anybody old enough? Yeah, we have plenty. So much engineering energy went into trying to figure out what to do with a damn keypad and how to, all kinds of clever sliding things, and they didn't pay any attention to the screen. And then, somebody, probably Apple, came up with a great idea of what if we didn't even have a keypad? And I think those are kind of the most exciting things, where it's like, all of a sudden this constraint, the keyboard, was gone, and the smartphones really took off after that. So what's the big constraint in databases? Well, the big constraint in databases is the table scan. And you don't have to take that from me. You can take that from the Oracle, who's invested more engineering energy in building fast databases than probably anybody. And they says, basically table scans are a nightmare. So what if we can remove that constraint? What if we can just make table scans fast? And so I'm going to start into a little bit of like how databases work to sort of build up into how we can make table scans fast. So the primary data structure for database is a B tree or a B plus tree, and it effectively works by building a tree of your data. So this select query that's doing a filter between these two boundaries, filter on this key, we're able to fetch that data doing only 5 lookups, because we only have to read these 5 blocks. And actually, chances are the top part of the tree is going to be cached, so it may only be 2 blocks. Problem is, what if you want to run a query that you can't filter conveniently on the key? Well, then you have to read the whole thing, and that takes a long time. So one way that people have tried to scale databases is they scale it out by basically taking a database and running it sort of in multiple nodes, and then with some lightweight coordination on top. I won't mention any competitors, but this is what a lot of people do. And there's a couple of problems with this. One is that you're limited to the storage that's attached to that node. So it's hard to scale that up. And the other one is, first of all, also like the coordination effort gets really difficult. In another session concurrently, where people are talking about BigQuery geospatial advances that we're launching today, and one of the things that does is you can do a cross join that says, show me the points from this table that are near the points from this table. In an architecture like this, that's super difficult, because you have to send all of this data between these nodes. So the network bandwidth becomes a big constraint. So what did the folks at Google do? The Dremel Paper came out 2010. Dremel had been around for several years before then. But effectively, the way they approached scaling was, we're just going to scale everything out super wide. So each one of these sort of boxes is a separate machine now, or is a separate task, or a separate container running in Borg. And we're going to make everything a table scan, because we have our fast distributed file system, which is Colossus. So you can read from hundreds of thousands of disks. We can read on 100,000 cores, and we can make this table scan fast. So we've been able to remove a bunch of database design constraints. There's the I/O constraints. Disks are slow. If you read from a small number of disks, that's going to be painful. Attached storage, you can only deal with the storage that's on that machine. CPUs aren't getting faster. Moore's law is sort of ended for CPU speeds. And there's also, as I mentioned, the network coordination bottleneck. So how does BigQuery do it? BigQuery / Dremel, because Dremel's the query engine that powers BigQuery. Well, it's going to read from lots and lots of disks in parallel. We have the separation of storage and compute, so you don't have any scaling bottlenecks. As you know, actually Lloyd and I were chatting yesterday. He says you can't fill it up. He says that, not me. I know how many disks we have, so like. And we can use thousands of CPUs in parallel, and we can use our, Google's very fast Jupyter infrastructure. So the Dremel architecture, as when we released it, sort of looks similar to that tree. This is a diagram from the original Dremel paper. But one of the things we soon learned when we released BigQuery is that log scanning is not data warehousing. People, if they're going to move their analysis onto BigQuery, we have to be good at data warehousing. So we made a big bet on dynamic query planning and optimization. And what this means is we will dynamically change the query plan depending on how that query runs, so that we can run it in an optimal distributed fashion. So 2018, this is sort of a stylized version of what the current architecture is. It's no longer a fixed tree. Basically there's number of stages. Each stage goes through a shuffle, which is a fast in-memory shuffle. And finally, you have the reduce at the end. And we can dynamically change how many shards we're using. We can dynamically change the whether we want to do a broadcast or a hash join. We can dynamically change how many stages, in fact, we're running. So BigQuery is a data warehouse. I'm going to try to convince you that BigQuery has, and I think a lot of other talks at Next have also talked about BigQuery as a data warehouse, and I'm going to go through some of the myths and how we've overcome them, or how those are not actually true. So one of the myths is, and I think this is even in some of our documentation that says, you should denormalize your data when you're using BigQuery. And now if you're in an enterprise data warehousing situation and you want to move your Teradata, or you want to move whatever your existing system is into BigQuery, you're like, well, I don't want to change my schema. I just want my old queries to run. So we understand that, and so one of the things that we've been working on, because for enterprise data warehousing, is you need joins to work fast. And so this is sort of how we've done this is the TPC-H benchmark. With 10 terabytes over the last 18 months, and so we've increased performance in the geomean. So we're not cherry picking individual queries to run here, but we've gotten 5x faster across the board. This is TPC-DS, which is another common data warehousing benchmark that is also increased by 5x. And I'm just going to show you, so that last little bit at the end, that dive down is a performance improvement that we rolled out this week. So can we switch over to the demo, please? So this is the TPC-DS benchmark, and this is sort of using kind of the old system, and I had this run. And we can see that it ran over 675 gigabytes, and it took a minute and 10 seconds. I'm not going to make you wait for a minute and 10 seconds while that runs, but I will switch over to the new version. The new version is exactly the same query. That's TPC-DS query 6, and we can run this. We can run this now, and it's run over the query is exactly the same. The only difference is it's running against sort of the clustered version of the tables, and I'll describe clustering in a couple of minutes. There we go. So 13.3 seconds versus so this is a 5x improvement, and this is just sort of the kind of thing that we roll out on a Thursday because it's ready. Can we switch back, please? Can we switch back to the slides, please? There. Okay, so now sort of we're advertising our best practice is don't denormalize if you don't need to. If your schema is more natural in the denormalized state, then by all means denormalize it. Or if the queries are simpler, or if you're doing joins against a large dimension table. So let's say you have a star schema, and you have your fact table, and then your other table is fairly large. You might consider denormalizing, but but that's also something we're working on, and we're working on. The reason I have an asterisk by large is because actually what large means is it should be increasing over time. And as I mentioned, joins have been getting faster, and they will continue to get faster. We've got a bunch of things on our roadmap that hopefully we're gonna continue to improve things. So I was chatting with Lloyd, my co-presenter here, a couple months ago, and he said to me, "I love BigQuery, but you guys need to improve partitioning." And we're like, yeah, we know. He actually didn't use didn't say it as nicely as that, but he approved this version of the slide. So the version of partitioning that we've had for a long time is ingestion-based partitioning, and I kind of just want to go through how this works so that I can show what we're doing differently. Excuse me. So BigQuery is a columnar store, or has a column store. So when you run a select, we only have to read we only charge you for the columns that you read. So in old BigQuery, we kind of read down the columns. But partitioning actually lets us do a slice across. So if you have a partition filter, we're using this sort of magical pseudo column that's based on ingestion time. But that does let you select only those bits and only have to pay for reading the data that's in that intersection, and only have to. So it's not just a cost, but it's also performance improvement. But so just recently we made column-based partitioning generally available. Column-based partitioning means you don't have to use this special pseudo column. This means that you can use a column in your table, and that's your partitioning column, and queries on that will just sort of naturally filter. But so that's great. That's been in the process for a while. That's not really going to move the needle for the most part. But today we're announcing clustering. And clustering, I think, is really pretty cool. And that takes partitioning sort of way beyond how it had worked before. And I'm going to just, when you have a table clustered, so you have your partition key, but then you also have your clustering key. And what a lot of people like to use is like a user ID or a customer ID. And BigQuery will actually store this in sorted format. SORTED, not SORDID. So when you filter based on that, you only have to read we can read a very, very small amount. So to give you just sort of an example how this works, so first we apply the partition filter, then we apply the cluster filter, and we only have to read a very, very small sliver of that table. So queries are going to be not only faster, but they're going to be less expensive. So clustering works with a high cardinality. Generally, you use it when you have a high cardinality field. You only pay for scanning blocks that match your cluster key. It's going to be faster, and it's going to be easier to manage because we have a lot of people that are kind of manually sharding their one table per customer. Now you can put that in one table and just do a filter, and it's sort of more natural data management. Switch to the demo, please. So I'm just going to start this. So last year, maybe it was 2 years ago, at Cloud Next, I ran this query over this giant petabyte table that we had. This petabyte table is a simulated retail schema, and we can see kind of what is in this table. It's got sales, and then you can join out to products. And so I'm doing a select star, which you rarely do in BigQuery because it reads all the columns. And this is doing a filter by key. So this is the clustering key. Now, one of the things that I didn't show last time was I didn't show how much this query costs, because when I ran it 2 years ago, this was actually a $5,000 query. BigQuery is fast and it scales, but you pay for that. So. We kind of like say, well, you can scale it to this, and many people who have this size table would be using fixed price reservations, so they wouldn't have to pay per query. But if you were going to pay sort of retail prices, that's how much it would cost. And when I ran this 2 years ago, it took 270 seconds. So I think it was almost 5 minutes. So we've made some performance improvements since then. And usually this takes, well, we'll see how long this takes. It's going to take a couple more seconds. I'm going to switch to the next one and come back to it. So that was just a scan filter query, and as I promised you, BigQuery is not just good at log scanning. BigQuery is also good at doing joins. And so actually last year, one of the things that I did was I showed how to do query optimization, and one of the things that I showed as an optimization was, okay, if your filter is on the wrong side of the join key, then or the join constraint, then your query can be really slow. So this is just showing that not only have we fixed that by being able to push the constraints through the query, but also now we can do, let's see, this query over the petabyte table, 3.5 seconds. We're actually doing a real join against a real table. All right, now let's jump back to this query, which finished in just under 2 minutes. So we're about twice as fast as we were 2 years ago. Things get faster. But one of the cool things is if you look at how much data we processed, it's 0.5 gigabyte. So this is what you pay for. So we've gone from $5,000 to this is about 1/10 of a penny. So this is what, like 4 orders of magnitude, 5 orders of magnitude price improvement. And back to the slides, please. So in case you're wondering, when to use partitioning and when to use clustering. So they are different. If you have a database background, people tend to be familiar with these terms. If not, it may be a little bit confusing. Partitioning is generally when you have a small number of distinct values. Less than 10,000 is our maximum for partitioning right now. Clustering can be any cardinality. You can have millions or billions of different values. In BigQuery, the dry run pricing for partitioning is exact. So before you run the query, we'll tell you exactly how much it's going to cost. For cluster tables, we're going to tell you the maximum it could cost, and if you have a clustering filter, it could be a lot less. That's sort of what you give up, and so the query pricing is exact for partitioning. It's best effort for clustering. So if you're writing a lot to your table, we may not have sorted it completely, and so we're going to charge based on whatever we have to end up reading. There is a small performance overhead for clustered tables per partition that you're scanning, and clustering doesn't suffer from any of that. But on the other hand, partitioning can be, you can do data management like it's a table. You can have expiration times on your clusters, on your partitions. Where on clustering you have to use DML. Okay, so I want to address some other myths about BigQuery. So one thing people say is, well, BigQuery can't do row and column level security. So we do it in a slightly different way. You can use authorized views. And so this has been available for a long time, but I kind of want to describe it because I think it's underutilized. So first step, you can create a view of the data that you want to share. And that could filter out the rows and columns you don't want to use or you don't want somebody to see. And then you add that view to the ACL of the source data set. Now what this does is it lets the person who owns that data set see exactly who has access. So we're not doing kind of delegated authorization or anything, and you don't have to worry about if the person who created that then leaves the company. You can audit, you can actually see what's on that ACL. So just to show kind of how this works on a typical table, let's say you have a phone number which has PII and you don't want people to see it, and maybe you have some sort of like special rows that you also want to keep private. So you just create a view definition that, let's say, it filters out the rows you don't want to show and hashes the phone number. And so the person, so by default, you can only see this view if you have access to underlying data. But so the next thing you do is you can add to the data set. You can say allow this view access to this table, and then you can share access to that view. So one of the things we like to talk about in BigQuery is just how easy it is to share your data, and we see this as a positive. Lloyd will also describe a little bit about that. But I was talking to somebody at a briefing in Texas, and he's like, well, easy data sharing, that sounds like a bug and not a feature. That means somebody can share it with somebody that I don't want it to be shared with. So Google Virtual Private Cloud is something that's in beta. And that's going to allow you to prevent, and so we could have kind of implemented something like this just for BigQuery, but this has actually sort of been implemented across Google's cloud using kind of standardized mechanisms. So you'll be able to prevent anybody from sharing your BigQuery data outside of your organization. You'll be able to define which services can be used. Like, so maybe you can, you can't export it to GCS. It allows you kind of to control the routes of data exfiltration and cut it off completely or cut it off to certain people or certain buckets. And you can also say that this can only be accessed from your organization's IP range. And so with like the virtual cluster, you can have stuff in your compute engine instances that look like they're from your organization's IP range, and so those will just magically work. Whereas some random hacker is not gonna be able to access. Another thing that people tend to want is they want to be able to control their own encryption keys. So BigQuery has a generally available feature we have since February that allows you to manage your own encryption keys. And so this sort of reduces the kind of debuggability from the BigQuery side. Like we can't go in and figure out what went wrong with the query as easily without getting explicit approval, and also it allows you to basically just be in control of how encryption is being applied. And so this is sort of how how the encryption works, and the final decryption actually happens all the way down on the storage layer, and the key material is never flows through the BigQuery servers, nor does the encryption or decryption happen there. So I also want to, with GDPR and with other, requirements, people want to have clean ways to manage their personally identifiable information and their PII data. And so I want to share a design pattern that one of our customers uses that uses encryption to control who has access to PII and actually remove it. So if somebody wants to be forgotten. So let's say you have a table with PII. This is sort of the basic table. The phone number column is PII. So you can encrypt that with a key. You can encrypt that with a key per row or per user ID. You have a separate table that has the keys that match up with each user ID. So when you read that, you can run an AES decryption, which is the new functions that we have to decrypt the data. And the nice thing about this is you can share this table with anybody you want. They can copy that table. You don't have to necessarily chase it down, but they can't actually read the PII in it unless they have access to this underlying keys table. And then if you for the right to be forgotten, or you want to get rid of that user, crypto delete is as simple as just doing a DML delete from that keys table. So you don't have to go back and figure out all the places where that PII went. It just it can now no longer be accessed. Another myth that is that people are worried that BigQuery makes it easy to run up a big bill. We now have self-service cost control. So I have one more demo, if you don't mind switching over, please. Thank you. And so I just want to show how this works. This is the Google Cloud Console. You can get here from where'd it go? IAM and admin and quotas, filter by BigQuery API, and you can change the allowable. If I can click on this. No. You can change the allowable usage per day. You can say edit quotas. Sorry, this is Lloyd's laptop. He doesn't have permission. But had Lloyd did, which I guess is a good thing. We don't want him to change our quotas. But had we had permission, we could just say edit quotas here for the BigQuery API, the query usage per day. and that gets applied immediately. So that's across your project. There's also a per user one that you can say. So if you want to say, each user should only be able to process 10 terabytes a day, you can set that. You can set that here. That one doesn't get applied immediately. There's a little bit of a delay, but at least there's sort of a self-service ways that you can manage that. Back to the slides, please. Something else that sort of a myth is that BigQuery doesn't allow enough DML updates. We do have batch DML operations, so often if people are used to do sort of individual deletes. You can delete from an array. You can delete based on a filter. You can delete based on a join from another table. But there's another really cool thing that's in beta right now is the SQL merge statement. And I wasn't aware of the SQL merge statement. And it's actually a pretty slick thing. So I want to go through how this works a little bit. So let's say we have a customers table, and let's say we have another table that has our updates, and we want to sort of apply those updates to the customers table. So the first thing we do is we start our merge statement, and we say we're going to merge, and we're going to kind of match those up using the user ID. And you can use complex conditions here. So then we match those. You can then define match conditions. So if there is a match between the two, so between the user ID on one side and the user ID on the other side, and you can even make those conditions arbitrarily complex. You can say also, if the table on the left is not locked, then we can do something, and the thing we want to do is update it to be the thing that's on the right. So fancy animation. We've updated that row. But you can do more with a single statement. You can also say, well, if there's not a match, which means that if there's not something in the left table, or if there's something in the right table that's not in the left, you can. In this case, we'll say, well, we're gonna insert that into the left-hand table. But wait, there's more. We can even say would not match by source, which means if something is in the left table but not in the right table, we can apply complex conditions as well. We can just say, in this case, we're just saying delete. But this allows you to do sort of really complex, like read, insert, update, deletes, all in a single statement. All right. So I've tried to convince you that BigQuery is a great place to do data warehousing, but I think one of the things that I showed with the reason that I had the initial kind of removing constraints discussion was I think BigQuery is more than just a data warehouse. And of course, I'm biased. I've been working on BigQuery for 7 years, and Google pays me to say nice things about BigQuery. So Lloyd's going to come up and talk about sort of beyond just normal data warehousing and the kinds of things that he's been able to do. And so Lloyd is the inventor of Looker. He is a big kind of BigQuery aficionado. He's been able to push BigQuery really further than almost anybody that I've seen. So I think there's not anybody better to show what else you can do with BigQuery. Thanks, Lloyd.
Thanks, Jordan. So as Jordan says, I'm a bit of a geek, so I'm not much of a speaker, so I apologize in advance. I'm going to talk. I'm going to frame what you can do with BigQuery first. I've been trying to think about how to explain this for a long time since I actually started Looker, and I still never got. It's never been perfect. So this is a new way of describing it that I'm going to try on you guys and see if it makes any sense. In the traditional reporting world, I think of that world as 2D data and 2D information, and that answers questions about what happened. So a traditional 2D thing might be something like the New York Times. The New York Times is vetted every day. It's a digest of most of the things that happened in that day. You know that the information is accurate. You can bank on the veracity of the information, and it's important. A textbook is another example of a 2D report. And for most part, in enterprise, 2D reporting is what you run your business on. The SEC is very if you build a report and it goes to the SEC, you very much care about the accuracy of that. There's another kind of information, though, that's happened since the dawn of the internet, and I was lucky enough to be around at the beginning. And that experience, that 3D information, is something like, say, Google, where you can go ask a question and do some research about a subject. So the 2D information, here's an example. Suppose you're reading the New York Times and you see a new competitor, and you read about the company. Well, if you're interested in that, you know that it exists, but there's not a lot more that you can do with it, with that piece of information. And pre-internet, you'd run down to the library and look for other periodicals about it and see, or call people and see if you could find some information about it. But in the post-internet world, you go to Google and you type in the company name and you look at LinkedIn and you see how many employees they have, and you might look on Crunchbase and see who the investors are and who the principals in it, and you might look on Glassdoor to see whether or not the employees like working there and how it's going. So there are other ways of doing research about something to get a better picture, to get more perspective. So 2D is flat and accurate and perfect and super important because you can't run your business without that. And most of the time we think of data, we think of it in that way. But there's another way of thinking about data, which is the investigative way. And it really hasn't really these new tools like BigQuery allow that to happen. And what's important in that is that you have a pretty comprehensive source of information. So like the web, there's lots and lots of ways to look at it and to dig at it. And because of things like these new data warehouses like BigQuery, you can put all the data in one place and then BigQuery and things like BigQuery and Looker can actually do the research to find out information about that. And so the 2D information answers what happened. And the 3D is about diagnostics about why it happened, right? And you can extract data and with small data sets try to look at why something happened. So people have been interested in that for a while. But really to get a holistic picture, you need the whole data set. So that's what I think that you should be thinking about trying to build out a BigQuery. I'm going to give you an example of a 3D data experience. One of our Looker early customers was a hotel aggregator, and there was a marketing person, and they had a 2D report, which was they were looking at their user base, and they were trying to figure out referrals because cost of acquisition for this business was super important, right? In order to be able to drive business, they got to drive the cost of customer acquisition down so that they could then get them to spend more on the platform over time. So they had a little report. It was just a grid, and on the one corner it was how many bookings they had going across and how many referrals they had going down. And in the lower left-hand left-hand corner, there was a number, and it was big. So these were people who had never ordered but referred a lot. They had people who had ordered a lot and referred a lot. That was that. But what surprised them was the number of people who had ordered. Who had never ordered but referred, and they were like, "Were we getting gamed? What's going on?" And in a 2D world, you're kind of done. That's it. I got to go back to the data team to get it. But in a 3D world, they can click on it, which isolates the data. Basically, would isolate it to both of those constraints: never ordered and referred a lot. And they could then look at the detail. So it's isolation and drilling into the detail. And then they got a list of email addresses, and they said, well, they weren't an engineer like me, so they were marketers, so they were not afraid of actually emailing them and saying, "Who are you and why are you doing this?" And it came back, "I'm a taxi driver, I'm an airline stewardess, I'm a bartender, I'm someone who gets asked the question, where should I stay tonight?" Right? And that changed their business, right? That ability to actually walk around and drill into the data, to actually going from the 2D perspective through the 3D perspective gave them a chance to see more data, to understand why that was happening. I'll give you another example. So Looker, I've been working on Looker for 6 years, but I've been a CTO at a bunch of companies, and one of the companies I was at was I was the CTO of an online crowdsourced call center with 30,000 home-based operators, and my job was to make it so that everybody in the company could see data. So I built some special purpose tools, and we had this measure that we used called a CHUP. Now, who knows what a CHUP is? Let's see, a CHUP is a phone call where the caller hung up before it came to an operator, right? And so an operational measure that we picked was the number of CHUPs over the number of total phone calls. What percentage of calls were CHUPs? And then we would look at this over time, and in the middle of the day, we saw a big spike that said there was a bunch of CHUPs in an hour period. So we isolated it. So we were like, well, why are there CHUPs? And so the 2D report said there was a problem, but the 3D, but we wanted to do some analysis. So the way that you start to do analysis is you isolate it to that, you filter on the range that's there, and you start to dimensionalize it by different things. You can dimensionalize it by operator. Well, was there one operator who wasn't picking up? We were routing to them and they weren't picking up? No, that wasn't the problem. Was it one program? Did we get a whole bunch of phone calls for a particular program that we were answering calls for? No, that wasn't the problem. Well, let's isolate it by telephony switch. Oh, look, this switch is broken, right? And so by dimensionalizing the data and walking around the data, you can actually see it. And so these are the kinds of things you can build out of a modern data warehouse and a data platform like Looker. That's not possible before. So traditional data warehousing is all about the accurate report, right? It's all about getting the data right. So in order to do this, what you do is that you vet the data on the way in. So the traditional way of putting data into a data warehouse is that it's small and it's relatively small. The data warehouse is expensive. Storage is expensive. So what you do is you take your transactional systems and you vet it and you compress it and you put it into the database, and you know that the data is accurate so that once it lands in the warehouse. Right? The whole idea is get it in there, it's right. So the data team is working as the ETL team. They're the person that makes sure that it's there right. In the new data warehousing model, you land the data in the warehouse, and then you build models on top of that, and you code on top of that to make so that you can draw more together, so you have access to all of the detail, and you build what we say that you build a model against that data, so that you know that it's accurate, and when you pull it out, when you pull the data out, it comes through code as opposed to coming through the way that it went in. And so we've been working together with BigQuery for quite some time, and together we make this great platform that you can use to do this 3D experience in data. They invited me up here because I do wild things with BigQuery. I'm going to show you a couple of cool things. One thing that BigQuery is, so I end up, Looker works against almost every kind of database there is, but I really love BigQuery's SQL because it is amazing it's amazing how they've implemented it. And what's different about them is their array structures, the UDFs, and the nesting, as well as the ability to handle just astronomical amounts of data. But the structures and the UDFs and the nesting allow you to build stuff that you can't possibly build in a traditional data warehouse. And it all comes down to a piece of technology is that arrays and structs are really subtables on a single row of data. Has anybody here played with the arrays and structs in BigQuery? Oh, cool. And UDFs? Cool. It's super powerful. So I'm going to do a demo in a little bit. But everything comes down to the fact that I'll keep repeating. This slide is going to appear a couple of times. It's really important to recognize that in a table, a repeated record is really just in BigQuery a structure and an array of structs, and you can treat that as if it were a table. There are basically three kinds of UDFs in BigQuery. The obvious one is the scalar UDF. You can pass a string and parse something out of a string in a UDF, and you can do that in JavaScript or you can do that in SQL. But what's not necessarily obvious is that you can aggregate an array into a structure and pass it into a UDF and treat it like it's a table. And that that allows you to do is fork queries, so that you can take a stream of data, fork some of the data out, and do some really interesting processing and bring back the results. So all the aggregate UDFs follow this pattern. The array ag struct construct is really building up a subtable. So that creates an array of a structure, and then the UDF you pass that to a UDF, and the UDF does a select statement on it, and then passes the result back. Here's an example of a median function written in SQL. You'll notice that the median function does an array ag on the numbers that it's going to collect, and then an unnest of that array really turns that array back into a table in a select statement. Does that make sense? I'm going to do a demo with some interesting UDFs that I've built. I'm starting with a table that really consists of just 5 fields. It's a name, a gender, a state, a year, and the number of people that were born with that name, that gender, and that in that state with in that year. Okay, and so this is it's from the Social Security Administration. The data goes from 1910 to 1913, and it's pretty wild what you can find with just these 5 fields. So can we switch over to the demo? So this is Looker, and in the IDE, I've built a little model. So for each of the dimensions that are in the table, I've created a LookML dimension for the name, state, gender, year, and the number was an integer. I wanted it as a float, so I cast it. I've added a couple of other measures, a decade, which is just divided by 10 for the year. I've built a sum, aggregate, and a count. And let's go explore it. So and this is the Looker interface, the Looker Explorer interface. It's pretty simple. I can actually I can start with the total number and the name count, and I can run that, and I can just see how much data there is. So so there are 300,000 names, 29,000 different names, right? I could add year and look at it by year. Let's sort the year, and we go to 1930. Let's see. So down in, and then I can see this shows me the most popular names in 1930. So just building a little data model. What Looker is doing is that it's writing queries again and feeding them into SQL. So everything that we click on, it really ends up being just a SQL query. Now above are the UDFs that I built in for this demo, but basically Looker just writes SQL queries against BigQuery and returns the results. So you get access to all the data no matter what you're looking at. Let's see. So if I want to look at the most popular name, I can look at the name and then total number, and I can find the most popular name. It's James, John, Robert, Michael, William. Great. That's all terrific. I can add filters. Let's look at female names, and let's look. Let's do median year. So Mary, the median year for Mary is 1941. The median year for Patricia is 1951. The median year for Elizabeth is 1966. Now, in this data, it's kind of weird, right? I just have the state and the number of people that were born in that name with that year. So what the median calculation is not simply just just a simple median. It's a weighted median. I have to take a look at the median year is what year were there as many people born before as after, right? And I wanted to build an aggregate for this, which is I want an aggregate function that does that. So I built a weighted median function. And the weighted the median year is the median weighted. It passes the year and the number of people that were born in that year. And I've got a new aggregate that's in SQL. And so if I actually go look at the code here, it really is quite simple. I use that weighted median function as if it were a built-in aggregate function, which is really kind of cool. It's actually taking something pretty complicated and building me this new concept of weighted median that I can use anywhere. And let's take a look at how that function is created. So I built this is all open. Basically, all this is open source, so you can grab it and play with it if you want. So there's a weighted median function. Here's basically what it is, and it basically takes an array of it takes that array as input, does this calculation, and returns the results. Pretty cool, right? So, but you can do also all other kinds of wild things too. You can do let's actually filter this. So it filter this by state and look at Alabama. Oh, come on. Versus California. Let's pivot the state, and let's look at a graph of that. Now, again, all this is running as a single SQL query. Okay. So we can see that Mary in Alabama, the median year for Mary in Alabama was 1938, but 1951, we can see a little graph of what it was. Annie's kind of interesting because it was really popular in 1931 in Alabama, and it peaked in 1984 in California. So like maybe it was Annie Hall or something. I don't, so, and it's pretty wild what you can see in the data. Again, this is just one table with 5 columns in it and BigQuery on top and some UDFs. It's pretty cool, right? I think it's cool. and if you look at the SQL for if we look at the definition for this, we can go back and look at the back at the SQL here. All the stuff that's doing the thing, but really it's just a time graph UDF, and the time graph takes the data as input and returns an array of integers, which are the amount for the decade, and then it converts that to an image, right? So SQL is just returning an array of integers, right? And so that's pretty snazzy, right? Here's another interesting function that how am I doing in time? Actually, I've got another demo, but I'm going to skip that because I want to keep rolling forward. Can we go back to the... So nesting is the other thing that you can do with BigQuery that's pretty amazing. So the UDFs are really cool because you can build these aggregates and do all kinds of wild stuff with it. But nesting is the other thing that is pretty unusual in BigQuery in the scale. So very often in big databases, joining 2 large tables can be a huge problem, right? There are things that are really hard to do when you have a couple of large entities. So like figuring out co-occurrence in large tables can be very expensive. Navigating graphs of data can be very expensive, and nesting actually makes a lot of this stuff better and easier. So again, if you think about it, in a nested table, basically what you have is an array of structure, a record, which is essentially an array of structs that are stored in the table. Here's an example of what a nested table looks like. You have this is an order tables with order items. An order naturally if you've got an e-commerce store that has orders and you can order more than one thing, naturally you'll have an order in a traditional SQL database. You'll have an orders table and an items table, a line items table, or an order and an order items table. But in a nested situation, what you want is you can put those together because they don't work without one another. Right, and an order item really doesn't exist without an order, so that you can place it in it. And as we can see here, the structure here is an ID, product name, quantity, and unit price. That's an order item structure, and it's repeated within each order. So each of those is like a little subtable within the order. Why do you care about this? Well, first of all, efficiency, and second of all, computability. If you're trying to figure out what was bought together in a really large database, that's called co-occurrence, and you'll have a really hard time figuring out. Basically, you can join for free. So anytime that you have a nested table, it can be up to 100 megabytes in BigQuery. You can pass that off. You can use a UDF, or you can use another SQL query to process against that, or join against it, and that happens in a way that is super efficient. You'll be really surprised how fast things work. Nested data that you should look at are things like orders and order items. Sessions and events are really hard. So, one of the traditional things in SQL is in log data is you have somebody you sessionize your data. You've got your event data. You roll it up into a session. It's a traditional MapReduce problem, and then you're trying to figure out who logged in and bought, who signed up today and bought. That can be really tricky in a traditional data warehouse, but it's very cheap to do in a nested situation because you can join the data twice and find co-occurrence. Other places are user and attributes. What you don't want to nest is something that's not naturally part of it. So like the user is not really part of an order or an order items because the user might appear in multiple different orders. So you wouldn't nest users. Does that make sense? an unnested when you join a nested table, it works just like it does like you are joining another table. It looks complicated, but it's actually really simple. Let's take a look. In this case, wait a second. Sorry, I'm missing a slide. How did that happen? I'm sorry. This is what an unnest looks like. In the regular, I don't know where the slide happened, so I'm just going to skip. Sorry. Anyway, co-occurrence, graph navigation, supervision, summary tables, and that can be larger than a single row. Oh, there's the slide. Okay, this is the. I'm sorry, I told you I'm not a great presenter. Anyway, so this is basically what a normal join looks like. And this is what an unnest join looks like. They're pretty much identical. We're out of time. Looks like I'm running out of time. So Jordan, I'm gonna call it. Sorry.
Can I just?
Yeah.
Just wanted to put in a plug. We have a bunch more BigQuery sessions to talk in more detail about some of the other cool, like, beyond data warehousing things like BQML, which I'm sure you've heard lots about today, geospatial, etc., and the public data sets program as well tomorrow. I also want to say there's a bunch of folks on the BigQuery team here. If you see one over at the BigQuery booth in Moscone South, please give us your feedback. Tell us what you like, what you don't like, problems you're having, etc. Finally, I just want to say, BigQuery is even better with Looker. I want to thank Lloyd for being up here with me and being able to show what kind of stuff BigQuery can do. Thank you.